Colligative properties are characteristics of a solution that depend only on the number of solute particles and not the identity of the solute. Remember that a solution is made up of solute and solvent, so these colligative properties are going to only depend on the number of solute particles and not necessarily the identity of the solute. So when we're working with these colligative property calculations, we do have to examine the type of solute we have. If the solute is a non-electrolyte, then the Van 't Hoff factor I is equal to 1. If the solute is an electrolyte, then we're going to have to determine the number of solute particles that solute has, and then that number will become our I. So this is a table of the colligative properties with their formulas, and again, you just want to pay attention to that letter I. That is going to be the number of solute particles for our electrolytes. Let's take a look at an example. The freezing point of a pure solvent X is negative 6.4 degrees Celsius, but when 29.6 grams of sodium chloride are dissolved in 550 grams of X, the solution freezes at negative 10.8 degrees Celsius. What is the freezing point depression constant, Kf, of X? So this is an example of the freezing point depression colligative property, and we're going to start off with our given information. In that first sentence, it says that the freezing point of the pure solvent is negative 6.4. And the symbol for pure is going to be that little degree sign. And when 29.6 grams of sodium chloride is dissolved in the solvent, the freezing point of the solution becomes negative 10.8 degrees Celsius. It also gives us the mass of our solute, 29.6 grams of sodium chloride. And I want to examine my solute. My solute is an electrolyte, so that means that I have to examine the number of particles. Sodium chloride is made up of 1 unit of Na plus and 1 unit of Cl minus. So that means the I is equal to 2. They also give us the mass of our solvent, which equals to 550 grams of X, and they're asking us to solve for Kf. Alright, since this is a freezing point depression problem, I'm going to start converting my numbers. I know that the mass of the solute has to be in moles. So grams of sodium chloride on top, then grams of sodium chloride on the bottom. And this is going to equal to 1 mole of sodium chloride. And for my solvent, I need that in kilograms. So 1 kilogram is 10 to the 3rd grams. For my freezing point depression calculations, I do need the freezing point depression, and I'm going to use this formula. So delta T is equal to my pure freezing point minus my solution freezing point. And I also need molality for this formula. So molality is moles of solute over kilograms of solvent. All right, I have all that I need. So now I'm going to go ahead and plug it into my formula for freezing point depression. So the depression is equal to I times Kf times M. I have my change. My I is 2, my Kf is my unknown, and I have my molality. So Kf is equal to 2.4 degrees Celsius over molality. So this is an example of freezing point depression with an electrolyte. Let's take a look at another example. What is the vapor pressure in millimeters of mercury of a solution of 12.5 grams of aluminum chloride dissolved in 200 grams of water at 60 degrees Celsius? The vapor pressure of water at 60 degrees Celsius is 149 millimeters of mercury. So this is an example of the colligative property, vapor pressure lowering. And I'm going to start off with my given information. It's asking me to solve for the vapor pressure of the solution in millimeters of mercury. It also gives me the mass of my solute, 12.5 grams of aluminum chloride. I'm going to go ahead and convert my grams to moles. And I'm going to examine my solute. My solute is an electrolyte, and this electrolyte is made up of 1 unit of Al3+ and 3 units of Cl-. So that gives me an I of 4. It also gives me the mass of my solvent, and I'm going to go ahead and convert that to moles. And I'm converting my masses to moles because for vapor pressure lowering, I do need to work with mole fraction. It also gives me the vapor pressure of the pure water. So I have the vapor pressure of the pure solvent, which equals to 149 millimeters of mercury. Okay, so I'm going to start off by determining the mole fraction of my solvent, which equals to the moles of my water over I times moles of water plus I times moles of aluminum chloride. Plug in my numbers. The moles of water is 11.1. Now, water is a non-electrolyte, so that means I for water is just 1. So 1 times that number of moles. Aluminum chloride is an electrolyte, and we said that the aluminum chloride I is 4, so it's going to be 4 times so my mole fraction for my solvent is 0.967. Okay, so I have all that I need for my vapor pressure lowering. So I'm going to go ahead and plug into my formula. The vapor pressure of the solution is equal to the mole fraction of my solvent times the pure vapor pressure of the solvent. Plug in my numbers, and I can solve for the vapor pressure of the solution, which equals to 144 millimeters of mercury. So this is an example of the colligative property, vapor pressure lowering. Good luck and keep practicing.